Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Today I will explain about analog electronics instrument. There is resistant temperature detector or RTD. My name is Bima Dardaa with study number 0231184000006 with my lecturer of instrumentation system Dr. Suyanto STMT. And there is our content. First of all, there is an introduction, and we're going to basic and working principle, and the last is application. As we know, temperature control is important in chemical process. The rate of chemical reaction often depends on the temperature. If the temperature is not properly controlled, the entire product may become useless. And also in industrial process, temperature, process pressure and flow control are widely used in chemical industry in general and in process engineering in particular. Numerous process and sequences are bound to one temperature or can be supported by a specific temperature control application and thus made more efficient. The temperature control system used must be able to react continuously and quickly to change and stabilize the process. Resistant temperature detector, we're going had a problem. There is how to use RTD as temperature measurement instrument, and the aim of this presentation is study know how to use RTD as temperature measurement instrument, and the contribution is as a comprehensive learning of analog electronics instrument. First of all, the analog instrument is defined as the instrument whose output in the continuous of function time, and they have a constant relation to the input. Physical quantity like voltage, current, power, and energy are measured through the analog instrument. Most of the analog instrument use pointer or device indicator the magnitude to measure the quantity. Resistant temperature detector is a temperature sensing device whose resistance increase the temperature. An RTD consists of wire coil and deposit film of pure metal. RTDs can be made of different metal and have a different resistance too, but the most popular RTD is platinum and has a nominal resistance of 100 ohms at 0 Celsius. So, for the pros and cons, RTDs are known for their excellent accuracy over a wide temperature range. Some RTDs have accuracy as high as 0.01 ohm in 0.026 degrees Celsius at 0 Celsius. RTDs are also extremely stable devices. Common industrial RTDs drift less than 0.1 Celsius each year, and some models are stable to within 0.0025 degrees Celsius each year. Because an RTD is a passive resistive device, you must pass a current through the device to produce a measured voltage. This current causes the RTD to internally heat, which appears as an error. Self-heating is typically specified as the amount of power that will raise the RTD temperature by 1 degree Celsius or 1 milliwatt per Celsius. RTDs can be difficult to measure because they have a relative low resistance at some 100 ohms that change only slightly with temperature less than 0.4 ohm per Celsius. To accurately measure this small change in resistance, you may need use special configuration that minimize the errors from lead wire resistance. Compared to the other temperature device, the output of the RTD is relatively linear with respect to the mirror temperature. The temperature coefficient called alpha differs between RTD curves, although various manufacturers may specify alpha differently. Alpha is most commonly defined as the change in RTD resistance from 0 to 100 degrees Celsius divided by resistance at 0 Celsius divided by 100 degrees Celsius, whereas R R100 is a resistance of the RTDs at 100 degrees of Celsius, and RO is resistance of the RTDs at 0 degrees Celsius. For an example, 100 ohm platinum RTDs with alpha 0.003911 will measure 1 and 39.11 ohm at 100 degrees of Celsius. Figure 1 display a typical resistance temperature curve for 100 ohm platinum RTDs, and this is the graphic. The resistance against the temperature is relative linear. Uh, whereas the resistance of the RTD at temperature T, RO is the resistance of the RTD at 0 degrees Celsius. A, B, and C are the calendar Van Dusen coefficients shown in the table 1, and the T is the temperature in degrees Celsius. For the temperature above 0, C coefficient equals to 0. Therefore, for the temperature above 0 Celsius, this equation reduces to a quadratic if you pass a known current Ix through the RTD and measure the output voltage developed across the RTD. VO, you can solve for T. There is an equation to solve the T. And also there is a 6 key or 6 factor difference between RTDs and thermocouples, because RTDs and thermocouples are designed differently, having a specific characteristics for it makes it impossible to conclude whether RTDs or thermocouples are the superior choice for a specific application. First of all, the first factor is measuring range. The main advantage of thermocouple is the range. Most RTD sensors are limited to the temperature of up to 400 until 500 degrees of Celsius, and in some cases higher, where certain thermocouples can be used to measure above the 1400 to 1800 degrees Celsius range, which makes them suitable for a large range of applications. And the second factor is accuracy. RTDs provide the highest accuracy and may to be prevent solution when temperature measurement accuracy is required to be around 1.1 1. Excuse me, 0.05 to 0.1 degrees Celsius. And the third factor is sensitivity. Although the thermocouple sensor system usually has a faster response time due to the changing temperature at its point of contact, it generally takes a longer to reach thermal equilibrium. This is largely due to the presence of the cold junction condensation, which does not respond to the change in temperature as quickly as the hot junction located at the tip of the sensor does. Its comparison RTD sensor is designed to be more durable and react faster than thermocouple. The fourth factor is drift. The RTD sensor has a small drift due to their design, which makes them produce stable readings for a longer duration than thermocouple does. And the 5 factor is single point measurement. Due to the design of a thermocouple, it's possible to narrow the measuring point down to the exact spot where the two metals are welded together. This point can be defined very accurately when operating thermocouples with naked tips or no casing. And the sixth factor is cost. When it comes to cost, thermocouples are generally less expensive than RTD sensor, as most thermocouple cost between half to one-third of an RTDs. And the last content is RTD's application. This is a PID controller tuning for glycerin bleaching process using well-known tuning formulas. The reactor tank was the most important part of the process plan, as this is where the process variables are measured and controlled. This figure is a simplified diagram of the physical arrangement of the reactor tank. The closed-loop block diagram of the temperature control system, as shown in this figure. The percent of color reduction of the glycerin is directly related to amount of heat released inside the reactor. Therefore, the percent color reduction can be also maintained by desired value by controlling the temperature in the reactor. The temperature or crude glycerin in the reactor has to keep the low as possible to minimize fatty matter increase from heating operation, but high enough to yield the desired final product. However, it depends on the characteristic and quality of the crude glycerin. In this case, the desired temperature level was set 850 degrees Celsius under suitable agitation speed. Uh, in this case, we use RTD as measurement temperature. The summary is an RTD or resistance temperature detector is a sensor whose resistance changes and its temperature changes. The resistance increases as the temperature of the sensor increases. The resistance against the temperature relationship is well known and is repeatable over time. An RTD is a passive device and it does not produce an output on its own. External electronic devices are used to measure the resistance of the sensor by passing small electrical current through the sensor to generate a voltage, typically like 1 milliampere or less. Measuring current 5 milliampere is maximum without a risk of self-heating. This is the reference that I used to make this presentation, and thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.